All right, it's 2:02 now. Let's get started. So hello, everyone. Welcome to Ask Seminar Series. I'm John, the seminar coordinator. I will be moderating the seminar with our communication specialist, Cassie Medley, and our associate director, Ralph Ferrero, also join us, and Ralph will be introducing the speaker. Just so you know that the seminar is being recorded, and we will publish the video recording on our YouTube channel. It usually takes a week or so, so please feel free to check it out. And after the presentation, we'll have the Q&A session. So please feel free to bring up any questions you have. You can unmute yourself, or you can, if you don't have a mic, you can chant out your questions. Before we get started, let me turn this over to our Associate Director, Ralph Ferrero, and he will be introducing the speaker. So Ralph, please go ahead.
Yeah, thanks, John. And yeah, I'm excited to introduce our speaker today, Professor Tracy Twine. She's Associate Professor, University of Minnesota's Department of Soil, Water, and Climate. She does a lot of research involving the Earth's surface and ecosystems. And let's see, yeah, she's developed a global vegetation model. And as some of you may have heard, she's got her PhD at the University of Wisconsin, has worked with a lot of colleagues that a lot of us know. So Tracy, welcome, and I look forward to your talk.
Thank you. Thanks, Ralph, and thanks everyone for joining. Am I still heard and seen okay? And you can see my slide?
Yep.
Okay, great. All right, thanks. Well, thanks everyone. I'm excited to give the seminar. I lived in College Park for a couple years in the mid-90s, so wish I were there. It's definitely better to talk in person, but I very much appreciate you hosting me here today so that I can talk to you from Minnesota, where it was a little bit chilly this morning. So Minnesota is really, it's a fun place to live and work for a weather nerd like myself and others, because we just have a lot of wild weather that seems to be getting wilder. The residents of Minnesota love talking about the weather. I mean, there's a lot to talk about, and it really affects our lives very directly. So there's much concern about day-to-day weather, as well as how climate is changing here in Minnesota. I mean, we have tornadoes, we have blizzards. There are some times when in our county with warnings, there has been a tornado warning and a blizzard warning in the same metro area at the same time. And we've got all kinds of extreme rainfall, all kinds of snow. We have shipwrecks, wildfires. There's a lot to talk about here. And so citizens are very interested in how our climate might be changing in the future. So I'm going to focus today on what my research group has been doing and looking to the future of Minnesota. But really, a lot of what happens here in Minnesota is an example of what can happen mid-continent, upper Midwest region. And so I hope that you'll find something useful out of this. So to get started here, let's see. Okay. So Minnesota is getting warmer and wetter like many other northern regions. And it's warming at rates greater than the rate of global warming. Here in this image, I'm just giving you some examples here. This is flooding on the Red River. It's in our northwest border of the state in 1997. So this region typically floods every spring from snow melt. Over on the right is southeastern Minnesota, and that is just a flash flood from a summer rainfall. Down, and the bottom two images here are just from a couple weeks ago. So we've already hit 88 degrees here 2 days in a row, which broke daily records by like 5 degrees, I think it was. And then we dipped down again, and it snowed some more. And then finally, as the snow started to melt, This is near Duluth at a state park, where that water is much, much higher, and it was lapping over that bridge. And just a couple hours after this image of these people on the bridge were posted, the DNR, Department of Natural Resources, then closed the bridge until the water could go down. So just a few examples of what the weather here in Minnesota can look like. And to look climatologically, according to the DNR, Minnesota had 3 of what they determine they call mega events in the last 30 years of the 20th century. So from like 1970 to 1999, there were 3 mega events. The first 20 years of the 21st century, there were 8. So more than double these mega events. So we are projecting Minnesota weather to get more extreme, not just warmer and wetter. One unique data set that we have here at Minnesota, right on the St. Paul campus, is a record of soil temperature since 1963. So it was installed by Professor Don Baker here. So just kind of behind where he's standing, they installed thermocouples at these 3 depths of soil, like about 3-meter depth, 6-meter depth, and almost 13-meter depth. And so they've been recording that soil temperature since 1963. You can see the trend is pretty much the same at all of those levels, but it really acts as a low pass filter, burying this under the ground to see that warming trend. And it's about 0.047 or 0.049 degrees per year from that. I imagine if we look a little bit more recently, this is from the Baker and Baker paper 2002, we'd see that trend increase, which is what we're seeing in our air temperature measurements. So this table here is showing us that Minnesota's warming. It's warming faster in winter than in summer. And in fact, winter is warming 13 times faster than summer. And we can look at an average change per decade in the middle here since, I can see my laser pointer here. Here's an average change per decade since records really began in 1895. But since 1970, you can see that trend is increased, and it's much, much larger in winter than in summer. So while warming's mainly winter phenomenon here, now kind of zooming out and showing you the state. This is looking at a total temperature change from 1895 to 2019. Here's our annual average change in temperature. Here's our how winter lows have changed total over this time period, and how summer temperatures have changed. And this is kind of broken up into these arbitrary 3 regions of the state. It's a tall state, and so we have more warming in the north than in the south. So you can see that warming in winter. Little to no change really in summer so far in terms of the length of the record. And just looking here at Minneapolis, St. Paul region on the left, this is a climate central map here. Minneapolis is one of the fastest winter warming cities in the country. So the lows that we had, the really cold lows are happening less frequently. The lows are no longer low. And we have a forest research station in Grand Rapids, so that's kind of up to the northern eastern side of the state here. And when they counted the days with minimum temperatures that were minus 35 degrees Fahrenheit or lower, you can see it when you bin them into the decades here, how they dropped off in the middle of the 20th century and then have really gone down. This is kind of an interesting figure here. It's the length and the magnitude of the 10-degree Fahrenheit season. So this slide is used a lot for public outreach. So we've got the units of Fahrenheit here. But it's looking at Duluth. Duluth, it's showing us just how the extreme cold season has dropped off. So this period here from 1959 to 1978, so kind of this 20-year period here. This is on average when the daily average temperature is 10 degree Fahrenheit, and going up it's how many degrees below 10 degrees. So you get colder as you go up. So it's a little odd here. But basically, you look at this mountain of coldness from the beginning of winter to kind of towards the end of winter there. And that 10-degree Fahrenheit season was 45 degrees long. Now, if we go to the next 20-year period and average these daily temperatures, so from 1979 to 1998, you can see the drop. So it doesn't get much colder, that much colder than 10 degrees Fahrenheit anymore. And now we're down to about 38 degrees. 38 days of this season. And when we go to the next 20-year period, 1999 to 2018, you don't see anything because it's completely disappeared. So this is one example of a city here in Minnesota where that really cold season shrinking in magnitude and in the duration. So our growing season, that time between the last freeze in spring and the first freeze in fall, that is lengthening. The sap running season of sap for maple syrup in our trees, there's anecdotal evidence that that's shifting, might be shifting earlier by a month in some locations. And this here is showing us the season of lake ice. So a lot of recreation going on here in Minnesota. And all these different colors here are just showing you a unique lake. And so going back as far as we have records for, you can see these trends of the days of ice duration declining as we get to more recent times. And then from about the 70s to recently, you can see that trend increases with much greater decrease in that duration of ice on the lakes. So Minnesota is getting wetter everywhere across the state and in all seasons. You can break this down, average it over the state and look at this table and break it down over the seasons. You can see our total precipitation change just increasing all seasons. Look at it across the state here in these different regions, it's increasing. Here's the average change per decade by that. It's getting wetter everywhere. In 2016, there was a town that broke our state's record annual precipitation with 56 degrees that year. Only 2 years later, this record was broken again in 2018. So this increase in rain is coming from an increase in storms and extreme precipitation here. Storms with more than 1 inch are increasing, not just Minnesota here, but across the whole upper Midwest, if we look at decade to decade here. And climate models project these trends to continue. So kind of looking here at this region where Minnesota is the upper Midwest, the winter average temperatures are projected to increase drastically. Here, the summer too is projected to warm. So that's not something that we've seen in our records here in Minnesota yet. Precipitation, winter precipitation to get a little bit wetter. Summer precipitation, maybe not so much, but then again, these are averages and not the extremes. So my research group looks at these projections from the global climate models, and we wanted to know if we could be more specific about how Minnesota climate is changing, and if we can help inform the various sectors of the economy in our state who have an interest in how climate might change. So to look at some of these impacts from projecting our climate, first we wanted to know, are these projections, how uniform are they across the state? And so our state is broken down into these 4 ecological biomes of conifer forest, deciduous forest, this prairie grassland over here, and this tall grass aspen parkland. So these are the 4 ecological biomes. They leave out a lot of water and a lot of people. Minnesota has the most peatlands in the country outside of Alaska, and most of these peatlands are unaltered. So they are in. This is from the National Land Cover database here. They are in this kind of pinkish purple color here. So we've got wetlands. we've got, of course, we've got 10,000 lakes. So all the blue here you can see are the lakes across the state. We have urban areas that are shown here in red. This is Minneapolis, St. Paul metropolitan area, but hopefully you can see that we have other urbanized areas across the state. And then all of that prairie land, the prairie grassland over to the west, most of that has been converted to agriculture. So that's something else that is impacted very much by not only natural and anthropogenic climate change, but by the human management itself. So we've got that. We have a lot of recreation year-round here. So here's Lutsen Mountain Ski Area, where they are concerned about decreases in snow and what that means in the future. Now that area, not far from Duluth, just experienced its snowiest winter on record. So they actually have a whole lot of snow this year, leading to some of that flooding that I showed you. But we want to know, what are the trends? What can they expect? We've got a lot of golf courses across the state. We've got this project now looking at how snow mold grows under mold grows under the snow and can damage golf courses. So knowing what to expect can help golf course supervisors prepare for the future. I have some colleagues here looking at this black line demarcates the conifer forest that's shown in green here, and the deciduous forest more over in white here, and how tree species are projected to change in the future. There's deer, and these invasive earthworms are interacting along with climate change to really alter the natural tree species that are growing in our forests here in Minnesota. And then we're interested in looking at drought and floods in agriculture and in forests, natural forest, and see what that might mean for the future as well. So we've worked with entomologists. This is me here on the left, trying to see what if Minnesota climate is getting more conducive to the brown marmorated stink bug. So that's something that out there with you in the east is a really big nuisance. It's only been observed in the Twin Cities here in very recent years. And once it gets into buildings and can stay warm over winter, there's a lot of concern about what that might mean, not only for a nuisance for people, it could also be a crop pest as well. And then other colleagues are looking at invasive weeds. These are just two examples here of some weeds in Minnesota. And these color maps here are showing the climate suitability for these weeds. So if you look at the real yellow color here, that means that climate is good. This weed is going to do really well. So they're interested in the winners and losers of climate change. This one example up here is doing well, but and then with the future projections here of 2050, it actually becomes more suitable in the northern part of the state for this weed. So that's not good. Whereas this weed that does really well now is projected to do not so well with climate change. So those are some questions that these colleagues of mine are asking. And then to look at humans, if we get to humans here, we drive on the roads and we have potholes. Potholes are costly, and more freeze thaw means that we will have more of them. And we apparently just had our decade's worst pothole winter here. And this is where they're dangerous to drive through. They're dangerous to swerve around. My husband was just talking about the pothole slalom team warming up as they're trying to get around these. So we've got that from freeze thaw. We've got pavement that can buckle from heat. That happens here in Minnesota as well. These are some pictures of that here. This image here, I don't, it's quite detailed and tiny here, but this is just an image from a report from some architectural colleagues where they're looking at building design, and building designers are looking at what a typical meteorological year looks like when they're designing buildings for the future. And what they average all the years here, and that's what this red dashed line is, and that heads out here to the right. These are the projections of climate. And so there's not, cool years, warm years, wet years, and dry years are all accounted for up here. but not in what these designers are using. So they really want some updated metrics of climate to design these buildings that are supposed to survive, 50 years or more. This headline here is talking about schools last year having to, a couple years ago, sorry, go to distance learning. So they closed down the final week of school due to heat. So this is just the year that students came back from being home from the pandemic. They're having all kinds of end of year festivities, and it all got canceled because of heat in Minnesota. Not the cold that also closes schools here. And so then again with heat here, the metro region here in the gray has the highest risk for dangers of heat to humans and other creatures. But you can see that most of the state actually is susceptible at some point to risks from heat. So what we did was we want to project future Minnesota climate. We dynamically downscaled some global climate model projections from the CMIP-5 data set. I'll tell you how we did that, and then I'll give you some highlights of how we're using them to look at these impacts. One of them looking at crop response to climate change here in Minnesota, and then looking at some extreme heat projections in Minneapolis. So we dynamically downscaled 8 of the CMIP-5 global climate models. We used WRF, so just a single regional climate model to take these coarser global climate models, see if we can get some finer information at a 10-kilometer grid resolution across Minnesota. Each model has a bias, so we bias adjusted monthly air temperature and precipitation. And we ran this model for the last 20 years of the 20th century. We did a mid this century scenario, and then we did an end of century scenario with this RCP 4.5 kind of a moderate emission scenario and RCP 8.5 a higher end emission scenario. I just want to point out that each model is going to have a bias. So we adjust them so that we're sort of starting from the same place when we then try to project into the future. So if you have questions on this, I can talk later. But basically, I just want to show you that all these little gray lines here, this is looking at temperature in the models, are all the various runs of temperature across the year from January to summer and then to December. We average all those models and we bring them all down. We average them to what we call a multi-model mean. We take each one of them and we try to remove the bias as compared to observations, so that we're all kind of starting out with what our 20th century observations look like. And then we run the models into the future, and then they will go from there. Models can differ in how they project what's going to happen to climate. But basically down here by the end of the century in this lower right here, this solid black line is the average projections of temperature. This is averaged across the state here, and then the black dashed line here was your observations from the 20th century. So we're able to look at month to month, season to season, how an ensemble of all of these models downscaled to this higher resolution can look like. So now looking across the whole state as a whole map here, this is our historical run, what winter average temperature looks like. Colder to the north, a little bit warmer to the south here. And then we've looked at mid-century. I'm just showing you here what it looks like end of century with the highest emission scenario. So kind of like the worst case scenario that we could expect here. And where these darker red colors are, that's a 6 degrees Celsius increase in temperature. So those high trends we're seeing of winter warming are projected to continue into the future. Summer here, these are our average summer temperatures. And then again, this is what's projected for the end of the century. It's about 4 degrees Celsius. So we didn't have much of a trend in warming in summer so far in Minnesota's history, but that is something that's changing in these projections. So that's kind of a new thing to expect. And most of this warming is pretty homogeneous across the state. So our answer to, how uniform is this across the state is, at least summer warming is pretty uniform. We averaged precipitation also across the whole state, and this time series here is just showing us what our historical run of precipitation looked like. So this solid black line is just all of these, all these little gray lines are each individual model run. So we expect precipitation to be more variable than temperature. But when we average them all, looks pretty good, peaks in June, and then decreases to winter. So that's historical. And now looking at projections for the future, all these different colored lines are downscaled from the different global climate models. And then this black line is when we average them all. So there's some wetter models, there's some drier models, warmer models, cooler models. Every season is expected to be wetter in the future, except really July, which is kind of the same as what it is now. So again, getting warmer and wetter. Really the only significant increase in precipitation that we saw was in spring, a little bit in winter, mostly in spring. So here's a map of our historical spring precipitation. Here, with a moderate emission, we get some increase in rain in spring up here in the northern part of the state. But here with this higher emissions, we get over the spring an extra 2 inches of rain up in this northern region, and then in this southern region down here, and then into Iowa too. We also looked at snow depth. And so here's an average look at our snow depth through history. And here our models are projecting, this is a decrease here, this is -3 inches less average snow depth over winter in this moderate emission scenario. And then in the higher emissions where this brown is here, it's really a decrease of 5 inches. So snow depth will be less as it warms. The number of days with snow cover are also projected to decrease. So what we did was we just counted up the number of days when we had snow on the ground, and we defined that as being an inch of snow. And so where all the blue is here, you can see that's, this kind of moderate shade of blue, that's 30 days. So that's a month less fewer days of having substantial snow of an inch or more on the ground. And then by this high emissions, end of century, it can be close to like 60 days fewer of snow on the ground. So we've got warming that's melting snow, and then we also, if the snow's not there, we have an albedo change where the ground surface is less reflective, and that can contribute to some more warming as well. So just to summarize this climate part, we have continued warming in winter in our projections like we have in history, and but this warming now is projected to occur in all months of the year. This increase in summer warming is something that's new and something we'll have to prepare for. Many fewer days of snow on the ground. But what we saw going from the moderate emissions to the higher emissions is that things do really increase a lot as emissions increase. So everything that we project here can be mitigated with reductions in greenhouse gas emissions. It does seem possible for that. All right, so now I want to show you how we've used this climate data set to look at some impacts. So we'll move on to looking at how crops can respond to this. So Minnesota's been getting warmer and wetter. Farmers have already been adapting to these trends because that has shown on our historic record. But it really hasn't gotten too hot in the summer as I've just shown you. So we want to know what do these projected increases in summer temperature mean for adapting for our agri-ecosystems. The timing of this increase in spring precipitation that's projected is going to be important, especially to crops where spring rain is important. They need it to grow. Too much spring rain and you might have saturated fields where it's hard to plant or can really stunt the growth of some crops. So hopefully we can shed some light on this. So we took that climate data set of temperature, precipitation, incoming solar radiation, and we ran it through this agro-IBIS model. This is mostly the same land surface model that is in the WRF CLM crop model. And we use this to simulate the growth and functioning of corn and soybean across the state. It's a mechanistic model, so it's got land surface, it gets information from the atmosphere, it actually grows the vegetation, and we'll look at biophysical and biogeochemical variables across the land surface. Up in this upper left here, it's just showing you what each model grid cell looks like. So we have a couple levels of canopy, a couple levels of layers of soil, multiple layers of snow and soil here. And so the model will take input from climate. It will use what vegetation is growing there, properties from the soil, and then all kinds of human management that can be represented in the model to simulate the growth and functioning of natural and managed ecosystems. So here are results of our simulated corn over the last 20 years of the 20th century. So so we started off with our 8 downscaled global climate models. Only 6 of them had climate that was conducive to growing crops. And then of those, only 3 of them simulated reasonable historic yields. So when we took what the model predicted for corn and soybean yields and compared that to what's reported from the USDA of what actually happened, only 3 of them really were able to capture reasonable yields. And so this green here is kind of showing us our yield of corn in megagrams per hectare. But what you're seeing is a simulated yield at each model grid cell through this. So we're going to use these 3 models then that were able to work and give reasonable yields in the past to move forward in making these projections. So here's simulated yield for corn and for soybean from these 3 models. So these aren't different time periods or anything. These are just all averages, differences in yield, but from the end of the 20th to the end of the 21st century at the high emissions. But we're just looking at the same kind of projection from these 3 different models. And the good news is that there's not a significant, little hatch marks here are statistically significant changes. And we don't see statistically significant decreases. You see a little bit down here in soybean in South Dakota, but it's not too bad here. There's really hardly any significant change at all. Soybean shows some increases here, a little bit of decreases there, and a lot of increases in this model. So because of the model being a land surface model, we can also look at energy budgets and water budgets. And so this is simulated evapotranspiration change from those same runs. So here, hatching again is statistically significant. So there's some increases in ET from that increased spring rainfall and water use of the crops, about 15 to 30 millimeters per month increase. Summer, one model showed a decrease there in ET. And then we can look at total runoff too from each model grid cell, and that has decreased here in this model. This is quite a dry model here. But so the runoff is down, but you remember it didn't really happen. It didn't really have too much of an effect on the yield, which is good. So some of these complications here from crop modeling is that we can, other studies have found some pretty large variances in simulated yields from different models and different data sets. And that downscaling and bias correction can introduce more variability here. So limitations here, but our results show that we did have large variability in projected crop yields, but it really do provide a lot of evidence that Minnesota might be in good shape for adapting to these. So farmers have been adapting to them, and this model allowed those crops to lengthen their growing season and take advantage of that warming and it didn't really dry out, obviously, enough to impact those yields. So that's hopefully a positive impact that we have here. All right, so that was the crop example. Now I want to move on to giving you an example of our extreme heat analysis. So extreme heat is the leading weather-related cause of mortality in the US. So I want to show you how we use this climate data set in an urban setting to see how heat events might change in the future in our Minneapolis-St. Paul region. Scott Sheraton and colleagues created this spatial synoptic classification. So it's very similar to kind of our standard air mass classification, where we look at how air masses move across different regions of our country, and they're represented by either being warm or cool or dry or moist. So for extreme heat, we care a lot about this MT, moist tropical air masses, and MT plus, which are sort of an enhanced, like a really, really warm, humid air mass. And dry tropical too, not as humid, but also really can bring the hot temperatures into regions. And the DP here, this dry polar, is what provides that relief, once those heat events move out. So I think our big concern, around the upper Midwest would be how the DPs and the MTs and DTs sort of battle it out. So each National Weather Service site in the country can be mapped to one of these SSCs, synoptic classifications. This map here is just one example. It's for June 28th in 2021. And then you see the little legend here on the right of different colors for the different air masses. So this algorithm uses air temperature, dew point temperature, surface pressure, wind direction and speed, and cloud cover to map a particular classification at each location. So by this time of year in June here, you can see the warm and humid SSCs are dominating really the eastern half of the country there. That gray color denotes a transition. So that's a day when one air mass is moving out and another one is on its way in. So that's considered a transition. We created, and I say we, this was led by my student, Jonathan Burkle. He looked at just summertime air masses in 4 cities of the state. I'm showing you Minneapolis as an example here, and we've defined our long summer as May 20th to September 10th. So this is just using historic records here. This plot here sort of shows you month by month what the frequency of these SSCs are right here in Minneapolis. So you can really see dominated by a kind of moderate warmth and because kind of dryish warmth and the humid warmth that's there. The table here is showing us a frequency along with some air temperatures and dew point temperatures throughout the day. It's kind of showing us that we really have a lot of dry polar that provides this relief from the warmth, and the moist tropical summertime humid air masses, and then these two are kind of the ones that we're concerned about, the hot dry tropical and the hot and humid enhanced moist tropical. So that's what our history looks like. We wanted to see then how the frequency of these might change in the future. So looking just at historical trends from about 1948 onward to now, this is a frequency in Minneapolis of these moist tropical days, so the MT days. You can see that increasing trend of them. And you can see this corresponding decreasing trend of the dry polar. So the warm humid air masses are increasing, at the expense of these cooler, drier air masses. So it's becoming warmer and more humid over time. What we really didn't see a significant change in are the frequency of those air masses of concern, the MT plus, the really enhanced warm humid ones, and the DT, the really hot ones. And that makes sense because just looking at our record of temperatures, we haven't seen that increase in really hot days in Minneapolis. But these humid air masses are creeping up here. So heat events happen over a several day period. So we looked at the duration of these heat events as periods of 3 or more consecutive days of the DT or MT plus days. And so again, there's really no significant trend in the frequency of them historically. We did see that those heat episodes lengthened a bit from 3.5 to 5 days on average. So a little bit longer than the past, but no more frequent. So this is just historical here. Then we used our our climate projections to try to see, can we take the climate data sets that we projected and run them through the algorithm to project what SSCs might look like in the future here in Minneapolis. So we here's Minneapolis here. So we took our climate data from the grid cell that contains Minneapolis, and we ran those variables through the algorithm to make a projected data set of SSC. The key limitation here is that we didn't assign any transition days because we didn't have some kind of fancy spatial temporal way to know how the weather was moving. We didn't do that. So that means we won't have any kind of projections in transition days. The left side here is just the same figure from history that I just showed you. The right is our projections from the model, but it's our historical run, so kind of our baseline. This is what's simulated here. So I just want to point out here, this is the difference where you're not going to see these transitions because that's something seen in the observational record that we can't simulate. So that just means those transition days are going to be spaced out then, and we'll have a little bit more of our other days. So overall, the model does pretty well, I think, in getting the main MTs and DMs that dominate the summer. It overpredicts the DT just a little bit there, but in general looks pretty good. So here's what our projections are for the future here. So let's see. So left here is our historical run, and then we have the middle of the 21st century, the end of the century with our moderate emissions of 4.5, and the end of our century with our high emissions of 8.5. So we are continuing the trends of decreasing the dry air masses, and both kind of our dry moderate and our dry polar, the really cool one, are decreasing, and we're increasing MT. You can see the MT in this green here jumps up in the middle of the century. That's its largest increase, and then it kind of remains here. And we see this MT plus, that's our extreme heat one, increasing towards the end, while this DP decreases to almost nothing here. So that DP, the dry polar air that brings that relief from those heat events, is declining in frequency. So here's our projections of our heat event frequency and duration. So left here are looking at those consecutive days, the 3 or more days of this oppressive heat. And you can see that here's a historic run of about 1 on average. So it about doubles by the mid-century, and then triples, and then quadruples. So the frequency of these events is projected to increase, even though we haven't experienced that in Minneapolis so far. Most of these episodes remain within the 3 to 7 day duration, so we're not seeing a significant lengthening of that, just an increase in the frequency of it. So conclusions here are that we found Minnesota should continue to grow warmer and wetter, And this is going to be in all seasons now, summer too, not just in winter. We'll have significant impacts to snow and our lake ice. Our cropping systems do show some adaptation potential to this climate change to maintain some yields. But our heat events are projected to increase in Minneapolis and in other urban areas. I just showed you Minneapolis as an example, with a decreased frequency of these cooler and drier air masses that bring us the much needed relief. So I want to give some acknowledgments to my team here, many of them who led these studies, Dr. Stefan Lees running the models, and Jonathan doing the SSC analysis. I want to thank my funders down here on the bottom. And then for what we're working on currently and into the future is updating these climate projections with CMIP6 data. We're looking at the future climate and what might be expected for golf course turf, really from Minnesota to Norway and to Oregon, kind of on those northern areas where golf courses happen to be in a lot of freeze-thaw regions. And we're working at a finer scale and smaller domain up north in, we have this 1854 treaty region where we're engaging with some tribal communities and focusing more on lakes and kind of trying to simulate through depths of lake what we might expect in the future as far as that goes. So thanks very much.
Thank you, Dr. Twine. So now is the time if anyone has any questions to either raise your hand. Oh, Andy's beat everyone to it. Go ahead.
Well, yeah, first, thank you for a very interesting talk. Just the other day, the senator from your neighboring state, Ron Johnson, said that climate change might be good for Wisconsin. You agree with him?
I do not agree. And I read that, and yeah. Yeah, and I would say that there are some legislators here in Minnesota who have made the same statements. Yeah, no, I don't. No, I don't agree with him.
Yeah, I guess if you're talking about potholes and weeds, that's one thing, but it actually looked good for corn and soybeans, right?
Yeah, I don't. Yeah, and I wouldn't even say that it looks good. I feel like it's optimistic because it doesn't look bad, and it is one sector. I mean, agriculture it's here because of humans, you know, and we have breeders who are breeding cultivars that can grow here. So I mean, that's good. That's like human ingenuity, you know, trying to overcome a problem. It's not necessarily a good thing. It's good that you can overcome the problem with this solution. But what I want to stress is, yeah, that's like a good outcome, that look, we can do this. But you know, that model doesn't account for pests or hail, or you know, things that are out of control from what we can manage, but you know, could be due to our, you know, global fossil emissions. Yeah, it's not good, and our winters are we're never. My colleagues in the state climatology office say, you know, we're just never going back. You know, we can adapt, and maybe it'll be, you know, we'll be okay. You know, we don't have to be so, you know, doomed that we're not going to be here. But the winters of Minnesota's past are gone, and it will have to be a new kind of winter.
Any other questions? You can, go ahead, Dave.
Yeah, hi, thanks. Very interesting talk, having grown up in Minnesota in the bad winters. It's nice to see those will be less severe. I've worked in forest ecology, and CO2 fertilization is really hard to pin down for forest processes. Is it pretty well established in that crop model of the fertilization effect of increasing CO2 on productivity?
I did account for that in the model, and so I was at University of Illinois before coming here, and I worked with some colleagues there who had the empirical data from actually growing crops under elevated carbon dioxide, and so I could take those parameters and put them into my model. And it, one thing it does is if you increase the CO2, the plants close their stomata because they don't need to take in as much CO2, and that helps them conserve water. So if you're under a drought, that could be a good thing. What I've just shown you is that we're going to get lots of rainfall here in Minnesota, so that's not necessarily a problem. And so the plants actually do respond well to increased CO2 in reality and in my model, but it's very much less significant an effect on it than what the climate change projection is. Things like moisture stress and the heat that are going to happen are all projected in all models to more than outweigh any benefits from CO2. So I would say, that is accounted for in these models, which is good. But that doesn't solve the problem because the climate change has a stronger impact than the CO2 will.
Okay, thank you. Thank you very much.
Thank you. There's also a request in the chat for the slide with the extreme rainfall trends to be shown again.
Yeah, sure. With the extreme rainfall trends, was that slide 12, the heavy rainfall. Let me see.
Maybe you can predict and James can say if this is the one that you wanted.
Yeah. Is it this one?
James?
Yes, that's it.
Okay.
I missed it the first time. It zipped by me.
I understand. Yeah. For time, I kind of, can't spend too much on each one, but each one has a lot of information if you dig into it. So this is all relative. If you look, it's the frequency relative to the 1961 to 1990 average. So that's sort of the period we're averaging over. That's why it's, negative early in the 1960s, 1970s, and then goes positive there.
Okay. No, we have a data system here at the Goddard Earth Science Data Information Services Center that we look at a lot of precipitation data, and so I'm always curious what can be seen. And there's a specific, I believe it's the North American Land Data Assimilation System that has extremes as an actual data product, and so I'm curious to see how what it says compares to what actual data like this says.
Yeah, and I admit I haven't looked at the data from there. But yeah, that is nice to have because you don't.
Well, it's hard to pick up extremes. It's hard to pick up extremes unless you actually have a data product tuned to looking at extremes, and that's why we want to publicize it a bit.
And it's sort of subjective too. Yeah, you're welcome. Thanks. And how you bin them too. Here we simply went,
yes,
inch by inch. But how do you,
per day,
sometimes you'll see 4 inches or more. Yeah. Yep.
Any other questions while we still have Dr. Twine with us? Okay, well, thank you everyone for coming. Thank you so much to Dr. Twine for giving us this great talk. As always, we will have a recording of this talk up on our YouTube channel by the end of the week. And please come back next week as we continue with our seminar series. I believe next week is our penultimate seminar for the semester. So almost done. Thanks, everybody. Have a good day.
Thank you.
Thanks.